You guys ready? So terminal voltage, lesson 7, last circuitry lesson. The terminal voltage is the voltage that you measure between the battery terminals, which is never quite the same as the voltage that's printed on the side of the battery. So printed on the side of the battery might be 1.5 volts. We're not going to get that. In fact, it turns out that inside every single battery, and this is what you can write down, there's actually an internal resistance. There is no perfect battery, which is both a bad thing, Rob, and a good thing, actually. You lose some voltage going through that internal resistance. V equals what times what? V equals what times what? Okay, so because this is an internal resistance, and we do want it to be as small as possible, typically we label it with a lowercase r for little resistance. And what that means is you're going to, I'll call it V loss, you're going to lose that much traveling through the battery. So this battery shack might say 1.5 volts, but you're only going to get 1.4 or 1.35 or 1.32. In fact, the bigger current that you send through, the bigger I times R loss is, the less actual terminal voltage you get. Does that make sense? You with me? What if you send no current through? What if I is 0? What would I times R be? 0. What would the voltage loss be? That's why if you just hook a voltmeter up to this battery, it will say 1.5 volts because no current is flowing. You're never going to get that. As soon as current flows, you lose a little bit, sometimes a bit more. Some terminology then. First of all, to show you that it's an internal resistor, usually we tend to go like this. You can write this down. We have our circuit, we have a resistance, and then there's our battery. Right now, there's no way for you to tell, hey, is that resistor inside the battery, or is that resistor like a separate appliance? So to show you that it's inside the battery, either we'll put a little dotted line like this to symbolize the battery case, or we'll put big dots like that to symbolize the terminals of the battery. So if you look at your ultimate review questions, for example, if I look at some battery pictures, oh, here, there's a great example. Only I notice here, in your picture, I put the internal resistor by the negative part. Here, they put it by the positive part. You can make an argument, Mr. Dueck, shouldn't they put it in between? Yeah, we don't do batteries that way. Anyways, I'm telling you that this is the internal resistance. I also made sure we used a little r to show you that that's the little tiny internal resistor. As opposed to this battery here, where we're in our magic physics world and there is no resistance, just to keep the numbers nice. We call the actual voltage that you measure, this voltage right here, from here to here, the terminal voltage. And I usually write it as V term. The reason is I've been using VT for V total, and I don't want to get confused. In fact, I've already decided next year I may change some of my abbreviations. Okay? And here is our terminology. First of all, there is current flowing through the cell. And because this is going through the cell, this is probably I total, unless your cell has more than one battery. Little r is the internal resistance. Now, this symbol, that's this symbol right here, is the maximum theoretical voltage. This is what's printed on the battery. It's sometimes called the EMF, not EMF, it's EMF. Unfortunately, it's a badly named idea because EMF stands for electromotive force. Boys and girls, what's force always measured in? Newtons. This is voltage. I told you some of our electricity terminology is archaic. They didn't know it wasn't a force when they named this. They called it electromotive force. And we still use the symbol, but so that we don't use the word force, Mickey, I say EMF instead. Hopefully you're not looking at your phone foolishly again or anything like that. No? Okay, it looked like you were looking down at something. So, this, the EMF, is constant, never changes, because it's printed on the side of the battery. Otherwise, when you plugged this in, magically the writing would change. Okay? And it is the maximum theoretical voltage. But because as soon as current starts flowing, you're going to lose, you're going to have a little V equals I times R, that's your voltage loss. What you really end up with is the EMF minus I times little r. In fact, this is the EMF minus I times little r. And that's called the net or the terminal voltage. And actually, this works in our ski hill analogy. How many of you gone skiing? When you get off the chairlift, don't you actually lose a tiny bit of height because you have to ski down a little ramp before you get to the hill? That little bump at the end of every chairlift, that's like our little voltage drop going through the battery. That's like the internal resistance. Now, where the analogy breaks down is, in real life, that ski hill, that little bump doesn't change. It's always the same height. Here, if current gets bigger, you lose more. But in terms of my ski hill analogy, this is my EMF, my maximum theoretical voltage, my constant voltage. This right here is I times little r, my voltage loss. And this height left over is my terminal voltage, what I'm actually getting. There is an equation on your formula sheet, although I tend to find it redundant. I think I can solve this whole thing always, Naomi, by skiing. But if you want the equation, here's what it says. Your terminal voltage is equal to your maximum theoretical voltage before you hook anything up. But as soon as you hook something up, now you have current going through the battery, you're going to lose voltage. You didn't write voltage. Yeah, I wrote IR, that's voltage. I times little r. Someone have their formula sheet? That's exactly what it says there, isn't it? Or what? Plus or minus? Oh. You know what? We're going to look at the plus. The plus actually is when you're recharging a battery. Okay? The plus is when you're recharging a battery. Oh, you missed my punchline? We'll fit another one in there somewhere. Next page over. So, example 1 says this. What happens to the cell voltage? And what I mean by that is the actual terminal voltage, what we actually get. Because look where the voltmeter is. It is on either side of the terminal. If we close the switch so that the current drawn by the circuit increases. What happens to the current? Why? Because I told you. First of all, ready? Scribble, 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 scribble. I didn't need to tell you that. And I'm going to show you how that in brackets wasn't necessary. Argument the first. Step 1. When I close the switch, I add a resistor in, thank you, close swith. When I close S, I add a resistor. Here's the key. Do I add the resistor in series or in parallel? Can I abbreviate parallel that way? When you add a resistor in parallel, what does that do to your overall total resistance? Bigger, smaller, or stays the same? Smaller. And I know this sounds weird because you added a resistor. How does that make it smaller? When you add it in parallel, you've opened another ski run. Trust me, you can get more skiers on. If you add it in series, absolutely, that makes your resistance bigger. So, our total decreases. Since I total equals, instead of writing V total, because that's going to look like V terminal, EMF, my maximum theoretical voltage, divided by R total. Here's the question. By closing that switch, if R total gets smaller, what happens to total current? Mark. When I divide by a smaller number, I get a smaller answer. When I divide by a smaller number, I get a bigger answer. So I total increases. Now, I really didn't need to tell you that in brackets. We just proved it. Okay? I'll leave it crossed out just to show you that technically, if I wanted to make this nastier, I could have had you prove that first. But you okay with that argument? Now, let's actually answer the question. It's saying, okay, what happens to the voltmeter when I close the switch? Does the voltmeter register bigger, smaller, or stay the same? Well, inside this battery, we know now there is an internal resistance. How big? Little r big. How many volts do I lose traveling through that internal resistance? Well, how do I find voltage? V equals what? It'll be I times little r is the voltage loss. I can make that neater. V loss equals I times little r. So in fact, I'm going to write that down here. V loss equals I times little r. And what did we say in point number 3? What was our conclusion in point number 3? What happens to the current when we close the switch? Okay. I increases. So if I gets bigger, what happens to V loss? Therefore, V loss increases. You lose more. So the terminal voltage decreases. Because instead of getting 1.5 volts, now you might get, so maybe your terminal voltage was your EMF was 1.5, and with the switch open, you're getting 1.46. Close the switch, 1.41. Or smaller. And you'll notice we answered that without using the actual equation. We skied. So example 2 says, find an expression for the terminal voltage where the cell supplies energy to the circuit. Okay. Yo.
Are you supposed to answer the question?
Oh, Rachel, so in my face. I didn't answer the question, Rachel. Oh, you made my day. Candy for you. After making fun of you for not answering the question, I did the same thing. How terrible is that? Absolutely. Absolutely. So, what's the terminal voltage? Well, first of all, if no current is flowing, it's equal to what's printed on the battery. And the symbol for what's printed on the battery is the EMF, the maximum theoretical. But as soon as current starts to flow, we lose voltage. How much? That much. Now, here's what else that means. That means that these three must add together to give me the terminal voltage. Huh? Well, trust me. There's the formula on your formula sheet. Again, Grayson, I really tend not to go with it. I'll show you both ways, but I prefer to solve it skiing rather than plugging and chugging. Let's do one with numbers. Okay? Example 3. I like this question. Actually, you know what? This is too easy. Mr. Dueck, now, by the way, I got the 2 dots, or we would also have the big battery casing, whichever way either of those says that little 2 ohm is the internal resistance. All right. It says find the terminal voltage. You know what? I'm going to find everything. And where have I always started? What have I tried to find first in any circuit? Total current. I don't see amps anywhere. Then I would go looking for any resistors where there was 2 things. Now, I had a student last class say, oh, Mr. Dueck, there's 2 things on this 2 ohm. It's 20 volts. No. The 20 is on the battery. The 2 is on the 2 ohm. Do I know 2 things on anything? No. How many resistors does this circuit have in total, grand total? 2? What type are they? Why, they are in... Oh. So, what's the total resistance of this circuit? Right? What's the total voltage of this circuit? And you'll notice I'm staying away, Joseph, from using that because that looks too much like V terminal. So I'm trying to, that's total, printed on the side, maximum theoretical voltage, which is what? Which is what? 20. Okay, so in this setup, V total over R total. That's 10 over 16. That's 5 over 8. Is it 0.625? Double check. Yeah, 0.625 amps. I'm telling you, since that's total current, this question's going to fall apart. And my first instinct almost always is to go to the top of my battery where people are getting off onto the chairlift and to say, okay, what that means is that this is 0.625 amps. Right? Oh, I can now tell you what the terminal voltage is. How high is the chairlift? Take away. What do I lose going through that little tiny resistor? Whatever 0.625 times 2, whatever I times R is, 1.25. You know what? I can do this in my head. 18.75? Is that right? In this setup, you would measure 18.75 volts across the battery. Why did I put amps? Because that's an upside down V with a slash. There. I don't know. Because I'm already moving on to the next question in my head. Teaching's tougher than you think. You split your brain. Have I told you? You split your brain in 3. Part of your 1/3 of your brain is about 60 seconds ahead. You pass it to the middle part, which says it. And then there's a part of your brain that double checks to make sure you said what you said, which is why you'll see me pause every so often and catch myself, because my brain's, wait a minute, ding, ding, but it's always about, you can see for me, a 5 or 10 second delay. Anyways, it's weird. Zach, you okay with that? All right, let's do some thought experiments. Some using principles of physics right to explain. Here would be some questions I could ask. Suppose I replace this 30 ohm with a smaller resistor. Would my terminal voltage be bigger or smaller? Well, let's walk through the argument. If this got smaller, what would happen to this answer? Bigger, smaller, or stays the same? Smaller. What would happen to this answer? If I divide Mark by a smaller number, what would happen to this answer?
It would probably get
bigger current. So what would happen to my voltage loss if this number got bigger? What would happen to this answer? What would happen to my terminal voltage then? Dropping, this is weird, dropping the resistance, actually you get less voltage, not more. And the reason is current went up. And so you lose more going through the battery. Flipping the argument, what if I put a bigger resistor here? This would be bigger, this would be bigger, this would be smaller, this would be smaller. My answer would be bigger. Now, that is how you can do this, Mac, without using the new equation that we wrote on the previous page. We used skiing. This next bit, you can write down if you want or not. Or you could have gone actually, you know what? Take it back. I'll do it on the next one. That'll work better. Okay. Example 4. In fact, this is really what I like. Probably in example 4, instead of asking you to find a terminal voltage, I'll ask you to find an internal resistor, because this is kind of useful. Here's what we're saying. You've set up a battery, and although the battery is printed 50 volts, you're not getting that. You notice you're getting 1.5 amps in this circuit. Hey, what is the internal resistance of this battery? Because now that you know that internal resistance, you could write that on the side of the battery. That's never going to change. Your EMF won't change, your internal resistance won't change, your terminal will, depending on the circuit. So this question says, find the terminal voltage and the internal resistance. Okay. Where do I always start? What do I want to try and find first? I got to be fussy. I always put a word in front of that. Begins the letter T. Okay, total current. Total current. Because any current won't help me. Total current. Did they tell me total current? Oh, okay. So I have 1.5 amps there. You know what? That doesn't help because I don't know anything else about that resistor. Keep skiing. Oh, how many amps do I have in this 30 ohm? Oh! Why is that so helpful? What else do I know? I know how many volts I must be losing going through there. How many volts? Zach, you're right.
Yeah,
45.
45.
Zach, what's my EMF, my maximum theoretical voltage? What's printed on the battery? What's the chairlift height? Those are all the same question.
50.
How many volts do I lose going through this big resistor?
45.
How many volts must I lose going through the internal then?
5.
And you'll notice, Joseph, I haven't used that new equation yet. I'm doing this all with skiing. Wait a minute. Zach, do I know the voltage? Do I know the current? Well, then I can find the resistance. First of all, they said find the terminal voltage. So what's the terminal voltage? What would I measure as a voltage right here? Gain of 50, loss of 5. What's the net voltage? Gain of 50, loss of 5. What's the net voltage? Okay. By the way, also you'll notice it's this voltage because this is the only other place that I lose voltage and it still has to get to 0. And little r is going to be V over I. It's going to be 5 volts over 1.5. What's the internal resistance? 3.33333. Okay. Is that okay, Mickey? Now, I'll write down, or if you want to, you could have done it this way. You could have gone V terminal equals E minus IR. You could have said, well, the terminal voltage is 45 volts. The EMF is 50 minus 1.5 times little r, and you could have got the r by itself. Minus 50 from both sides, divide by negative 1.5. I'm going to argue kind of doing it by skiing is probably cleaner. And you're not having to learn something new, although great. Where I do sometimes use this equation is when we're recharging. When instead of a minus sign, it's a plus sign. Like here. Now, how can you tell this is recharging? What do you notice about this diagram? What's weird right away? Two batteries, more specific, not only two batteries, they're facing each other. They're opposing each other. Okay. It says, find an expression for the terminal voltage. The cell is being charged. Well, now, if we were measuring this voltage, first of all, if this is the battery charger, it's forcing the current this way. This way. So your terminal voltage, if the current was flowing, look up, this way, you would say it was the EMF takeaway what you lose going through. But if we're going this way, aren't we going up the resistor? But here's why that's so handy. It turns out, Shaq, it's this little bit of extra voltage. That's what does the recharging. If you had no internal resistance, you couldn't recharge a battery. But Joseph, this also explains why it takes so long to recharge batteries. It's that little bit of extra trickle voltage. That's what's recharging the battery. That's why you can't just plug a battery in and then have it recharged. So I said internal resistance, it's kind of a negative in that, okay, you do lose some voltage. Oh, but it's a positive, because if I didn't have that, I couldn't have a recharging. We built a lot of our newer technology out of lovely rechargeable batteries, your phones and things like that. And it's that little blip right there. Hey, let's actually crunch some numbers. So here is a classic example. Here is a rechargeable battery system. We have a 30-volt charger, and we're recharging a 9-volt cell. 9-volt batteries, those are the rectangular ones with the 2 terminals on the top. If you touch them to your tongue, they kind of sting. You may have tried that. Go ahead, it's good science. Those are 9 volts. So we're recharging one of those. Okay. How many cells are there here? 2. What's the highest voltage? What's the highest mountain? Which way is going to be downhill? That's all the same question phrased differently. 30. Downhill is this way. And as soon as you give me 2 batteries, before I start, I want to make sure I know which way the current is going. Remember the 2-battery circuit that we solved the other day as well. So that's downhill, that's downhill, that's downhill. Okay. Now let's start. I always look for total current. I don't see amps anywhere. Then I look for resistors where there's 2. I don't see resistors where there's 2 things. How many resistors are there in this circuit? What can you tell me? What type are they? Oh, they're in series. Well, I think that means what's the total resistance of this circuit? Hello? Sorry? You're right. 11 ohms. Now, here's the trickier question. What's the total voltage? I'm going to give you a hint. How high is the biggest mountain? 30. But now we're going down the second mountain. How far? What's the net voltage? This is 21 volts. That's my total voltage in this circuit. And we did that last day, and the reason I did that last day was just for this question, so I can teach you how. You guys should know how batteries recharge. Oh. What's the total current? It's going to be total voltage divided by total resistance. 21 divided by 11. Don't all rush for your calculators at once or anything. Isn't it 1.91? Like, isn't it 90909090 or something? Yeah, let's go 1.91. I didn't do that one in my head. I remember that one from last class. Amps, not volts. So, how many amps right here? 1.91. Oh, how many amps right here? 1.91 amps. Could I figure out how many volts I lost there? Sure, I'm not gonna, but I could. How many amps right here? 1.91 amps. How many volts right here? I times R. Oh, 1.91 times 1. Okay. So, the terminal voltage, if nothing was flowing, would be the EMF, 9. Is there current flowing, though? Yep. Is the current flowing up the battery? So is the current flowing in the correct direction or in the opposite? The correct direction or opposite direction? Opposite. So instead of losing from there, you're going to be gaining from there. What would you measure with a voltmeter across that battery? 10.9 or 10.91 volts. And that's that extra 1.91 volts. That's what's doing the recharging. By the way, let's go back to this here. What if you had more current flowing through here? If current got bigger, what would happen to this number? Bigger or smaller? Zach? If current got bigger, what would happen to this answer? I thought you gave me the answer. Sorry, you counted that? You zoned out? Really? Mac, if current gets bigger, what happens when you multiply here? It gets what? Bigger. So you'd actually have more voltage recharging. This is why some of you may notice different chargers have different amperages. I have a charger in my car's electrical outlet that has one prong that says 1 amp, another prong that says 2.5 amps. Which one do I plug into all the time? 2.5. I want my phone to charge faster. iPads also need the bigger charge as well because they got a different style of battery. My Android, my Note 4, comes with a quick charger. I need to look at this. I forgot to look at the plug. I need to, because it'll go from 0 to about 65% in about 45 minutes. Then it starts to slow down and take longer because it turns out Grayson and Zach, I think that's it. It's actually an exponential curve, and as you charge, it gets steeper. It's harder to charge the remaining parts because they're exponential. Looks like that. People that I have in my other math class. Okay. So here, terminal, I think all I wanted was, terminal voltage, 10.9. It's a gain. Just now, I could have also gone with the equation and plus, but again, Rob, hopefully I've showed you that equation is redundant if we just ski carefully. So, in summary, if the cell is supplying energy, if it's not being recharged, then V terminal equals what's printed on the side, the EMF, the maximum theoretical, the chairlift height, minus the little bump at the end of the chairlift when you get off, the internal resistance voltage drop. And if we're recharging, the terminal voltage will be the EMF, what's printed on the side of the battery, the constant voltage, the thing that doesn't change, plus that little bit. We're done. I said I was going to give you lots of time. Yep. What homework are you going to, what's the homework? What did I assign here? Rachel, this is the one that I had in mind from your question. So number 1 and number 2, specifically for number 2, DULP. That to me, I like that question, I like that question, I like that question. In fact, I think I'm going to give you one almost identical on the test, except instead of 4 batteries, I think I just make it 2 batteries because it's overkill. Or 3. I don't think I went the full 4. Okay? So 1, 2, 3, 4, 5. 7. 8. Those to me are all pretty fair game. 10 is probably tougher than I'll give you on the test. 10 is asking you to find the cell voltage. By the way, do you see an internal resistance or anything on this battery here? What you're really finding is the terminal voltage, but whatever. When I say find the battery voltage, if I'm not fussy, then good enough. Okay? 10, 11, and 12. And you can now do any question from the review. So what did I assign? I assigned 1, 2, 3, 4, 5, 7, 8, 10, 11, 12. Let me circle that on block G. 1, 2, 3, 4, 5, 7, 8, 10, 11, 12. You have a whole half hour. You should leave here with almost everything done and caught up and try and get a bunch of stuff handed in.